Hello, and thank you for coming to the talk. Today we're discussing how to integrate learning about cloud development and tools into a technology curriculum. This is a talk I'm calling Cloud from the Ground Up, a new approach to technology education. I will start this off with a little caveat that my experience is primarily from American universities, and therefore this advice is based on what I have seen in those systems. While it may be more or less applicable depending on how close your system is to an American system, to universities in other countries, I cannot guarantee that the information I'm about to give you is going to be accurate if you're teaching in another country, at least in terms of the current curriculum. So, what are the goals of this approach? Right? The goals of the approach I'm about to outline for you are to treat the learning of application development for local IDs and development for the cloud on the same level, right? We want students to come out with a core, comprehensive, well-rounded skill set. So it doesn't feel like they've learned all this development for local and then we're tossing the cloud on top, right? We want something that's a comprehensive setup for both types because cloud is increasingly an integral part of the development experience. We want to send students out into the world ready to work with cloud technologies and on systems without that being a weaker skill set than their traditional programming. We want to make them comfortable with the project lifecycle and larger development projects that often come with cloud development. The goal is for new developers, new computer scientists and software engineers, information technologists, to come out cloud ready without having to go through 6 months of new on-site training from their employer because their only development is in local IDs. So, the traditional technology education in a university setting. The traditional technology education, not shockingly, focuses primarily on local development environments, on students learning those fundamental skills of programming and then translating that into group projects that are usually, 3 to 6 or 7 students working on something more substantial. Some universities will talk and focus on the software development lifecycle. Some will focus more on project management theory like Scrum or Agile and how to work with a client. But that's about where they put themselves. Cloud, if it's introduced, is introduced in later courses, a junior or a senior level course, sometimes before students have their networking, and often in electives. So a student might leave one software engineering course on the cloud. There were 4 more, but they didn't choose to take them, right? And in terms of the actual kind of skills of object-oriented programming, usually a university will pick a language or two, so C or Java or Python, something object-oriented, one of the widely established languages, and use that to teach both the syntax of that particular language and the general structures behind object-oriented programming, right? And this is done on local machines for a couple of reasons. First and foremost being that if every computer in a lab is the same, and every set of lab computers in a department are the same, students don't have to be confused figuring out how to navigate multiple setups. Faculty can do demonstrations that should work on every student's computer because they all have the same machines. And it's easier for people like information management and for new software vendors coming in to do their jobs. There is value in consistency. In addition, for universities that have had longer running computer science departments that were maybe developed in the 60s or 70s, this is just how they've done things. And there is a certain amount of institutional tradition. If it's broken, they don't want it. If it's not broken, they don't want to fix it. And then cloud technologies are usually introduced later, like I said, in higher level courses, particularly in junior and senior year, and often sometimes more of that curriculum is covered in an elective than it is in core required courses, which is great if you happen to take all those electives, and problematic if you thought the history of computing was more interesting. You might leave school without a critical skill set. Most of what gets integrated into courses for the cloud right now is sponsored by platform providers. So like Google Cloud and AWS both have higher education programs that are fairly robust. when it comes to teaching students how to use their services, but because the curriculum mostly assumes that you will have been developing for a while, that you'll have had your first couple programming courses and data structures under your belt before your university is bringing you in for the cloud, they come with kind of the assertion that you understand the fundamental concepts of programming, right? The cloud becomes the kind of cherry on top of the ice cream sundae instead of its own unique setup and tool, unique approach to learning programming. So what would a cloud up approach look like, right? If we could wave a magic wand and change curriculum, what would it look like to integrate cloud from the very beginning in a technology education? First things first, we'd start with infrastructure. It's really tempting when you're making new developers to just want to be like, well, let's start with Hello World. Let's get you up and writing code as much and as quickly as possible. But if we're looking, to integrate the cloud into this, what we need to do is start with the hardware. Students need to know how the cloud works before they start trying to develop for it. Making sure they have a foundation, knowing what a server is and how they work, knowing things about networking concepts, knowing why redundancy is important. Things like this, that underpinning physical structure is important for students to understand kind of a lot of the core stuff and why we do things the way we do in the cloud. If they don't have that, we're asking them to figure out what the pie is without letting them taste it. So we should, in addition, talk about the core features and limitations of both development for the cloud and development for a desktop or mobile IDE. So what we're looking for from each, what the costs and benefits are for both. Are we looking for the fastest possible solution and a high distribution? Then the cloud might be our option. Are we working in an area, maybe in the developing world, where internet connections are going to be scarce? Then local IDEs might be our best option. Is there a security concern? Then a local IDE during the early stages of development might be something to consider, right? There's a case for it, even if it's not the ultimate choice. And in these early courses, we're going to focus on a single platform to work with students on, right? The emphasis here is this is one implementation of these relatively universal structures on cloud platforms. It's also worth noting that in a precursor, before they get to that, this is us using AWS, this is how we do that, students should probably in those very first courses start getting familiar with Git, right? Knowing how to push and pull, how to fork things, give students a market advantage when they start thinking about cloud development and working with other people. Step 2, we're going to start using small programs, not just as a way to teach the programming language and the concepts of OOP, but as a way to demonstrate the differences. Small, easily achievable projects. Our Hello Worlds, our calculators, our building a web store, things like that are not going to be large. They could be achieved in a week or two by a student programmer on both local setups and cloud systems, so that the student gets used to thinking about programming for the desktop and programming for the cloud. And yes, for some of these, for Hello World, the difference is going to be negligible. When you start getting to a web store, well, then it's going to be a little different, right? That's when we're starting to show how these things diverge and how that changes our critical thinking in regards to code, right? And this is to both reinforce the essential skill set of programming, right? Of knowing how to develop an algorithm and implement the code and debug it, and also to move them kind of towards the greater goal of this entire system and structure, right? We're trying at this level in step 2 to create a groundwork to help students compare and contrast models of local programming and cloud development, getting them thinking about how those types of development differ, what the outcomes are going to be, and why we want to do something one way in one environment, why we might choose to do something a different way for a different environment. Step 3, we'd be moving up to kind of mid-sized modular builds. We'd be moving into larger programming classes and projects where the focus would be on modularity of the program. How does a distributed system make this larger program work? We can then use this as kind of a compare and contrast with the structures of classes and objects in traditional OOP, so thinking about the flow of data through a program and the flow of data through a program on the cloud, to get them to understand that the modularity of structure is something that works on multiple levels. And the goal here is to keep an emphasis on those parallels, on what's the same, on what's different, on why we make the choices we do. right? Because ultimately, sending students out into the world with the idea of what something is or how to use that thing without knowing why and when they're going to use it, without having decision-making skills, isn't going to service them as young professionals. And once we've kind of got the fundamentals of programming, once we're past our recursive algorithms and our big O, and we've gotten data structures managed, right? It's time to start moving into an aggressive 2 years of projects. So this is coming into junior and senior year, where we're bringing students together to solve real-world problems in the cloud environment. We're putting students into large working groups, 10, 20, 30 students, and asking them to solve bigger projects than they would be able to with a more traditional school group of 3 or 4. Yes, this means whoever's supervising them, whatever faculty member's in charge, has to spend a little bit more time and energy managing the project, managing the students. What happens if student B is behind on something and student D's work is dependent on B's? How do we manage that project? How do we keep students accountable? How do we build a project management system into the class, right? And that's actually one of the benefits of this, is we can start slowly introducing students into things like Agile or Scrum, into project management plans, and getting them living in a software development life cycle, getting them used to the idea that there's going to be a meeting once a week. Here's the things we're going to be working on. Some of these goals might be flexible based on needs. Anyone who's ever worked in a project in the real world knows that things do not just go according to plan all the time. It's just not the nature of reality. So getting them used to adapting and working things through early on is probably one of the biggest benefits that we can do them. It'll help teach them resilience and adaptability in a professional context, in addition to giving them the opportunity to look at a development life cycle as more than a theoretical construct, and to understand how important things like communication are when we're working on a large project. Finally, in that, again, junior, senior year, we're looking to diversify platforms. Early on, when we're first starting to learn to program, we're picking one platform and we're sticking with it. We're just working on Google, we're just working on Amazon, we're just working with a Linux system. Whatever, right? Because we want to give them the consistency when they're learning fundamental skills. Moving forward into those upper grades, those upper years, we should be getting them experience with a wide range of platforms. This is good for both immediate career readiness skills and for developing a culture at your university where students understand that technology is going to change. They are entering a fast-paced career where they need to learn new things and stay on top of that. And then, making sure that these projects have a healthy dash of APIs and other tools that are critical job skills. It's really cool that you made this thing by itself, but maybe we can work in some maps? We could work in a map API, right? Or we could work in an API for an online payment system. Things that take advantage of and leverage what's already existing in a way that develops a portfolio. So when a student goes out to an interview and an employer says to them, well, have you ever done this? Well, I've done something like it. And they have an idea of how to answer how to do that thing and how to show what they can do. And then, finally, is this a perfect model? No, of course not. Perfect is never the aim for models in pedagogy. Our goal is iterative improvement. A little bit like making software. We're looking for things to get better and better and better and better. I am by no means the only authority on teaching in the cloud. And these are a general, broad-based, structured set of guidelines because different universities have different methods for handling things. And this isn't just a model that can work for universities. If you're working in a boot camp situation or professional development, this model is broad enough to be adapted. And that was part of the goal in its development. Anyway, thank you very much for coming to listen. I hope you found this to be a valuable use of your time. Thank you.